Hi, one of the difficulties of studying metric spaces is due to the lack of linear structure on them. There isn't a way to add or subtract points in the metric space, and there isn't even a notion of multiplying by a scalar. This result is claiming that if you have a separable metric space, then you can imagine that it is sitting inside a Banach space. In other words, you can produce an isometric copy of it inside that L infinity. So L infinity is the space of all real valued sequences that are bounded. And that supremum of entries is defined to be the norm. It's a complete normed space, so it's a Banach space. But L infinity itself is not separable. It's a huge space. So the way we prove this is we fix a dense subset of the space X. And the idea is that if you know the distance of a point to all of these individual AIs, that pretty much uniquely tells you where the point is. No two points can produce the exact same sequence of distances to each and every one of these AIs. That's the whole idea behind the proof. For technical reasons, we first fix an x0 in the metric space, and then we take x to basically the distance of x to all these AIs, except that we also subtract the distance of AI from x0. So the first entry becomes dxa1 minus da1 x0. The second becomes dxa2 minus distance a2 x0. This technical subtraction makes it well defined into L infinity. In other words, the sequence of numbers you have produced actually is bounded. And that comes from the triangle inequality. Distance of x from aj minus distance of aj from x0. This is basically the jth coordinate of ix, is bounded by dxx0, which is independent of j. So if you take supremum over j in natural numbers, you still have a bounded quantity, and that means ix does belong to L infinity. So that's just saying that I, as a function from your metric space into L infinity, is well defined. So we are ready to prove the main part, which is the isometry. To be an isometry, we must show that for every 2 points from your metric space, the distance of the images is equal to the distances of the points you started with. And since you don't have anything on the left-hand side to deal with, you begin studying the right-hand side and then do some calculations and hopefully end up proving the equality. So what is ix minus iy? So those technical part that we subtracted actually goes away in subtracting these two images, and you end up with the jth coordinate becomes dxij, dxaj minus dyaj. Against triangle inequality tells you that this is less than or equal to dxy. But this is for every j, and the right-hand side is independent of j. You take supremum, and that gives you that the norm, L infinity norm of ix minus iy, is bounded from above by distance xy. So that is 1/2 of proof. We have to reverse this inequality, and for that you take some epsilon positive, and you take, because of density, there is an aj which is even closer than epsilon to y. So there are arbitrarily close points to y, and you pick one of them, say it's aj. Then what is the jth entry of ix minus iy? That is distance xaj minus distance yaj. Now we want to do a bigger than equality, so I replace this underlined term by these two terms. Why can I replace it and have a smaller quantity? That's again triangle inequality. The beauty of metric spaces is all you have is triangle inequality, and everything basically has to follow from that. This is true because if you take dyaj to the other side, that is the usual triangle inequality. So x meets aj, and then aj meets y. Aj goes out. You get that you have bigger than distance xy. And then you copy the next item, which is distance yaj. But these are same, so two of those, and it's less than epsilon, so this is bigger than dxy minus 2 epsilon. So the most you can subtract is 2 epsilon. Therefore, already in entry j, ix minus iy is larger than dxy minus 2 epsilon. So L infinity norm is bigger than that much. But epsilon was arbitrary, and we have this inequality independent of other choices. Therefore, you can actually take epsilon to be 0, so you get this inequality, which together with the previous one proves that this is not in fact an inequality. In any case, it's always an equality, and that proves the isometry of this space. So as an exercise, this is kind of, it could be a difficult exercise as well. Try to embed the usual square, which is 0, 1, interval 0, 1 to power 2, or just you could say R2, inside L infinity. So according to this theorem, you must be able to do that because it's separable. But can you do it with hand? Is it doable, or is this result too abstract to give it? And the other simpler exercise probably will be, what are balls in L infinity like? So what do they look like? What is the shape of a ball? So for example, draw a picture of, say, ball at 0, radius 1. So with that exercise, I end this one, and thanks for listening. See you again soon with more metric geometry.